Hi everyone. So hopefully by now you've watched Beta's video. So in the second module, we will continue to study consequences of departure from classical physics. Quantum mechanics has a very distorted fame in popular science. It is described as kind of mystical and talked about in almost religious, new agey terms. Um, in reality, it is not mystical. It is very much grounded in experimental evidence. And the reason I wanted you to see Beta's lectures because he is one of the he's in the second generation of the founding fathers of quantum mechanics, and that lecture emphasizes really the connection to actual um, to actual experiments. It is meant to dispel these mystical perceptions out. However, it is true that quantum reality is hard to visualize. In our everyday life, we don't have direct experience with some of the aspects of quantum reality, such as uncertainties, wave particle duality, entanglement, and so on. Although all of these are affecting us in an indirect way. The world is definitely quantum, and the question of how classical description of nature that we're familiar with emerges in certain limits from a more fundamental quantum description of nature, that's a very deep and fascinating question. It's a much more advanced question. We're not going to touch upon that. So it's wrong to say that quantum mechanics is physics of the very small. It's usually presented like that. That's not really the right way to see it. In fact, there is no fundamental reason why macroscopic objects cannot behave in a quantum way. However, it is a very difficult thing to do. And there's a fundamental reason why this is a difficult thing to do. Some of the most frontier research, such as quantum computing, um, deals with this very issue of how to make um, macroscopic objects, basically things that are much, much bigger than atoms, perhaps things that we can even see with our eyes, how to make them behave in a manifestly quantum way. That's a very advanced topic of research. We're definitely not going to touch upon that. But there are some examples of macroscopic matter behaving in a quantum way that you may have heard of. For example, superconductivity. Superconductors are conductors. They're macroscopic objects. You can hold them in a hand, and they have very unusual electrical properties. And these electrical properties uh, owe their existence specifically to quantum mechanics. You cannot have that kind of behavior based on familiar physics like Ohm's law and things like that. Other examples are superfluidity. There's maybe you've heard of something called Bose-Einstein condensate, another example, and there are others. Again, that's a very popular topic of frontier research of exotic electronic states of materials that are that owe their existence specifically to quantum mechanics, another advanced area of research. Um, so once again, the question of how quantumness of nature gets hidden from our direct experience, that's a very interesting question in its own right. And while it's what I said is true that quantum mechanics doesn't have to be restricted to microscopic particles, um, it is more easily manifested in microscopic particles. It is much easier to see quantum effects with protons, electrons, and so on. So you might say, well, I don't care about these particles, electron moving through potential difference. It's boring, and I'm not a particle physicist. Why are you giving us particle examples? Uh, please understand that we're doing that because particles are a vehicle to understand foundations of quantum mechanics. We're not, we will not be talking about particles for particles' sake but rather because that's single particles or two particles is a simplistic situation in which quantum behavior can be understood at an introductory level. So we're using them as a vehicle to understand foundations of quantum mechanics. Sometimes I get comments, for example, in the evals that, you know, your lectures are aimed at physics majors, but you're not giving us things that are more relevant to us, electrical engineers. This is a misunderstanding here. My goal is not to aim lectures at a particular major. I'm very happy to have physics majors because it's true, they come, they ask very interesting questions in office hours, as do others too. But I'm not aiming at a particular major. I'm trying to capture as broad an audience as I can. My goal is to build foundation. So all of the topics that we do, they might come off as dry topics, but they are foundational topics. When you look at a beautiful building, you don't even see the foundation. You see the things that are on top of the foundation. The foundation is underground. It's not particularly interesting to look at, but without the foundation, the whole building would collapse. So the goal of this course is to build the foundation of certain ideas that are, by the way, relevant not only in quantum mechanics. And then when you move on, it will be easier for you to understand other things having built this foundation. That's what I'm trying to do. A couple of other remarks. Unlike relativity, quantum mechanics was not developed by a lone genius. It is a product of many monster minds and countless other ordinary minds. And moreover, as you may have, maybe this thought came across when you were watching Beta's lecture, that all the names, they're men. And it's true that in the past, science was mostly a boys' club. Not entirely, but mostly. But that's in the past. Nowadays, there's a lot of women working in both frontier and applied research in quantum mechanics, and that number is increasing. So times are changing. So if you felt like, well, what's going on here? Times are changing rather rapidly, and nowadays a lot of women are making contributions to very important subjects in both frontier and applied research, getting Nobel Prizes and so on. But like I said, quantum mechanics was not developed by a lone person. However, the standard interpretation of quantum mechanics, the one that we teach, also known as Copenhagen interpretation, is to a large extent a brainchild of Niels Bohr and maybe also Max Born. Bohr especially appears behind many of the ways in which we interpret the meaning of quantum reality, and his fingerprints are all over the way that we teach introductory quantum mechanics these days. So I wanted to make one more remark about the flow of this course from now on. So think of this course as like climbing a mountain. And so the mountain has the following profile. We started with very rapid, very steep climb. So that was relativity. Now it will relax a little bit for a few weeks. And then there will be another rapid, even steeper climb, and it will terminate at a pinnacle. So this is relativity. For the next 2 weeks, it will mellow out a little bit. It will still require a lot of thinking and watching and coming to discussions and asking questions. But it will not be kind of as much of a mind twister as relativity was. And then we will start doing sort of a real quantum mechanics. So chapter 3, So this is chapter 3 and 4. They're not actually quantum mechanics, they're introductory chapters. And the goal here is to get across the notion of wave-particle duality. So quantum mechanics is built on the experimental evidence that what we think of as particles, electrons, protons, helium atoms, they have wave-like aspects to them. And what we think of as waves, light, has particle-like aspects to them. And chapters 3 and 4 present that evidence, digested, and out of that will come out the notion of the wave function. So wave function is a way to describe quantum objects, which is opposed to the way that we describe classical objects by trajectories, positions, and velocities. So this couple of weeks will be build up towards the notion of the wave function. In fact, we'll get to it next week. And what that means, how to work with it, how to think of quantum things in terms of the wave function. And then we will begin using the wave function. We will begin finding wave functions in simple situations. And that's where a lot of math will come in. So the reason this will be a very steep climb, is because I'm going to have to teach you math in parallel to discussing physics. There is no way around it. There really is no way around it. So I'm going to have to give you a series of boot camps on complex numbers, on probabilities, on differential equations, so that once you've built up that muscle, lifting the weight would not be impossible. So this is the roadmap. This is where we are. It's going to get a little bit easier in the next 2 weeks, and then it's going to be a steep climb again. And the last few weeks is going to be particularly steep. This is how it is. I'm here to facilitate. I'm not here to make it difficult for you on purpose. And I just wanted to be upfront about what's ahead. All right, we'll start. We'll start tomorrow. We'll talk about photoelectric effect and Compton scattering, and that's really, well, there's another part of chapter 3 that we'll discuss next week, but that's the meat of chapter 3, where we present evidence for particle aspects of what we thought of as waves, light, for example. And that's part of the wave-particle duality. We'll do that tomorrow. Okay? Well, I'll see you then.